So far in the course, we've been talking about probability models for discrete random variables. Now, an example of a discrete random variable would be something like the number of heads that you get when you flip a coin 10 times. Now, usually when we talk about discrete random variables, we're talking about a finite number of outcomes, but not necessarily. The important thing is that a discrete random variable is a countable outcome. But what we want to do is now extend this and move on to a more useful category of random variable. We would like to talk about something called a continuous random variable. Now, continuous will generally mean uncountable here. And so as an example, this could be the number or the amount of time spent on a phone call. Now, our brains usually think about minutes and seconds, but in reality, it could be any smaller portion of a second. And in fact, there is really no limit to how precise we want to measure that. The capability of what we use to measure things will limit us, but as far as the idea goes, we can pick any particular value we'd want for time. So that's an example of a continuous random variable. So what we would like to do is generalize our ideas from discrete random variables to continuous random variables. So we're going to generalize all the concepts of discrete random variables to continuous random variables. And so really, how do we do this? And there's one key idea here, and we're going to talk about the mass function for a discrete random variable to try to give us a clue. And the title itself gives us a clue here, right? So let's talk about the mass function for some random variable x. So typically we think of a mass function as just essentially a table of values. And the random variable can take on a lot of different values, let's say up to xn. And for each value, there has to be an associated probability. Now, the really key idea here is that the sum of all the probabilities has to add up to 1. That essentially is another reflection of the probability axioms that we had. As we know, probability individual values can only ever be between 0 and 1 as well. So both of those things are important, and we're going to need them as we go. Now, I mentioned a second ago that mass is the key idea here, okay? And so the concept that I want to get across to us here is that probability you should interpret as equivalent to mass. If you keep that idea in mind, it will try to explain, it will help guide you through what we're going to talk about next. So we are going to interpret the mass function as a collection of what we call point masses. They like to use this term a lot in physics. It's basically something that occupies no space but has some mass. And so on this axis, if we talk about probability, and on this axis, if we talk about the x values, you could say, all right, x1 has some probability value p1. And x2 has some probability value p2, and x3 could have some other one, and x4 could be somewhere over here. So it's a collection of point masses. Now, if we have 4 of them, then we have a graph with 4, etc., etc., etc. The values of x don't have to be equally spaced. It could just be any value there. In order for us to generalize to the continuous case, what we're going to try to do is we are going to redistribute the mass from a point into a bar. So we're going to try to redistribute the mass from a point into a bar that has a width of delta x. And so this will be easier to try to illustrate to you in a picture. So if we just take the picture that I had above and say, all right, there's x1. It had some point mass here, p1. What I'm going to try to do is say, let's take all of that mass and spread it over a bar. So we're going to redistribute it. So we want to transfer it. And now this bar has a width here of delta x. Okay? And so we now get into an important idea. If the mass here is the probability, and it has a value of P1, so it has units of mass, we would like this to be equal to something. Okay, well, we're trying to transfer or redistribute that mass into a bar. Well, if that bar has a width of delta x, that means it has units of length. In order for me to get the units of this equation to balance, I need something on this side that has units of mass per length, which makes the length units cancel out and go over there. And so you may know from physics or chemistry or wherever this is what we call a density. Because density has mass per some measure of space. So we are going to call this f of xi. And so this will be what we call the probability density at the point x equals xi. And so if we were to go ahead and then do this for every value of x that we have, and just to make our lives easy, we'll assume that they all have the same width. We would go ahead and we would transfer all of that mass to bars in this sense. Now, it doesn't necessarily mean that you have to have the same width, but it will just make our lives easy when we want to talk about this. And so this concept is the key really here. So in general, that probability that's stored in the single mass point can now be written in terms of a density times some measure of space. So the total probability, or the total mass that's contained, would be the sum of all of those pi's, which would then be the sum, I equals 1 to n, of all of those densities times the delta x's. Now we know that this has to equal 1 because we talked about the fact that we've got a mass function and we've got that property from before. Now here's the key. As the number of outcomes goes to infinity, so we're adding in more and more and more of these outcomes, we are turning our variable from a discrete one with a finite number, a countable number of outcomes, into something with an infinite, uncountable number of outcomes. The total probability is then going to be a limit as n goes to infinity, I equals 1 to n, of the sum of all of these things. Now, you should have seen this thing before. By the definition of a Riemann sum, you know that this is an integral. And it's going to be an integral of f of x dx. Because we don't yet know what the integration limits are, to be safe, we want to capture every single value. So the generic notation is that we write it as an improper integral with negative infinity to positive infinity as the limit. And so this idea of generalizing probability as mass and therefore allowing us to extend the concept. This allows us to connect things to a probability density when we've got an uncountable number of outcomes. So we define what's called the probability density function. We'll call it a PDF, and it must satisfy the following. We've got to have something that's always positive. So our density function always has to be positive. Can't have a negative probability, can't have a negative density. Number 2, the integral of this function, when you integrate it over all possible outcomes, has to be equal to 1. And if you don't integrate it over all possible outcomes, remember that up here we talked about probability being equal to this integral. So if you are interested in the probability that your random variables between some numbers a and b, this would be easily calculated from the following. So we've got this new tool, the probability density function, and the density function is the right tool for us to be able to work with continuous random variables. If you were to have a density function, because it's a continuous function, you could plot the density function. And so density functions may have all sorts of pictures, but when density functions are higher, it means that these outcomes down that correspond to those that height are more likely, whereas when the graph is lower, the density is lower, the probability is lower, so these outcomes here are less likely. And that interpretation is going to be important for us. So from this point, this gives us a start as to how we can go ahead and work with continuous random variables. In the next video, we'll talk more about all of the ideas behind this and